In this video, we're going to start looking at Chapter 2, which is Motion in One Dimension. When talking about motion, we look at the branch of physics called dynamics. And this is the branch of physics involving any motion of an object and looking at the relationship between the motion and other physical concepts and what's happening to that object to make it move or to keep it in motion or to prevent its motion. And the first subset of dynamics is a subject called kinematics. And in kinematics, we're interested in the description of the motion itself, not necessarily what's causing the motion, but the description of the motion. Any motion will involve three basic concepts, and those are the three concepts that we're going to talk about in this video here today. And those are displacement, velocity, and acceleration. And we use these concepts to study the motion of an object. So first, let's have a very brief background of how ancient civilizations studied motion, and it started back with the Sumerians and Egyptians, and they mainly looked at the motion of heavenly bodies, talking about the stars and the moon and other planets. And then the Greeks came along and they also looked at heavenly bodies, but they took a more systematic approach and were more detailed in their studies. And they had a geocentric model, meaning the Earth was the center of everything. Then Copernicus came along, and he developed the heliocentric system that we use today. And what that means is just the sun is the center of our solar system. And then after Copernicus was Galileo, and he made more astronomical observations with his telescope that he designed, and he found experimental evidence to describe the motion. And he used that experimental evidence to quantify the motion that he studied. So we are going to continue in this Galilean or even Newtonian way of looking at physics, and Newtonian is from Sir Isaac Newton, and we'll get into some of his contributions later. But we're going to take this viewpoint in studying motion and overall studying physics. So to first study motion, we have to look at the idea of position. And to talk about position, we have to define it in terms of a frame of reference. So this typically means that we choose a coordinate system and we choose a coordinate axis. So we pick where is 0, where's our origin, and this basically defines our starting point for measuring motion. We have to have some starting point from which we measure to give a distance. And in one-dimensional motion, this typically is just on the x-axis or the y-axis. Not both. It's one-dimensional, keep in mind, so it's one or the other. Typically, we will pick the x-axis in one-dimensional motion, and we have this idea of displacement, and that is the change in position of an object. So an object may start at an initial position that we're going to call xi, x sub I for initial, and it will end at a final position that we'll call x sub f. And the difference between these two is our displacement or a change in position. And typically, the standard units that we're going to use are meters. Let's look at an example here. On the right, we have two positions of a car. We have position A to start, and then we have position B to end here. So our final position is at the 52 meters, and our initial position was at 30 meters, and that's describing the position compared to some 0 point. Now, in this case, we don't really care where 0 is. We're just picking a 0, and at position A, car is 30 meters from 0, and at position B, car is 52 meters from 0, so its change in position, or its displacement, is 22 meters. Now, one of the keys here is this displacement is positive. And what that means is that indicates that the motion was in the positive x direction. We went from a small position to a bigger position. So it's a positive direction. Whereas if we look at from C to F, we go from a position of positive 38 meters to a negative 53 meters. And that negative means we're to the left of the 0 point. And so our change in position from C to F is a negative 91 meters, and the displacement is negative, telling us that we move to the left or the negative x direction. if we look at these positions graphically, meaning we're going to graph each of these positions with respect to time. So on the y-axis here, this is our position, and on the x-axis, we have our time. And so as time goes on, our position changes. And we can learn a lot from this graph, and we're going to spend a lot of time delving into what exactly this graph tells us about the motion of an object. And it's very important to be able to interpret a graph like this, a position versus time graph, and give information about an object's motion. So in this scenario, the time that it takes to go from position A to B to C to D to E to F is 10 seconds. So they're constant intervals. And so the time that elapses from A to B is 10 seconds, this time right here. But we look at the change in position from A to B, and that change is the displacement that we found earlier, that 22 meters from position A to position B. So we talk about delta x is 22 meters, and delta t is 10 seconds. So the change in time is 10 seconds. The change in position, or the displacement, is 22 meters. We could find the change in position or the displacement from any two positions, A to C, A to D, A to E, or even D to F, any two positions. We could find the displacement and also the time interval over which that displacement occurred. In talking about change in position and change in time, we have to bring in the idea of vectors versus scalars. A vector is a quantity that needs both magnitude, which is talking about the size, so a number like 22 meters, and a direction to completely describe it. So when we talk about displacement, we say that it is a positive 22 meters. That tells us that it's in the positive x direction, that gives us direction, and then it has a quantity of 22. So we typically use the positive or negative sign to use our direction, meaning the positive direction or negative direction. And when we're talking about the x-axis, that's right and left. Typically we say to the right is positive and to the left is negative. However, if we want to redeclare our frame of reference, that could be switched. We could have left is positive and right is negative. Scalars, however, are completely described by magnitude only. An example of that would be time. When we talk about time, well, that's 10 seconds, 20 seconds. Is there a direction of time? Well, no, because time is always marching forward. Time is linear, and it continues to increase. So time doesn't need a direction. It's a scalar quantity. And there's many other examples that we're going to continue to talk about. But for right now, the idea of displacement, we will consider a vector quantity because it needs both direction and magnitude to properly describe it. Now, this is a big distinction that we need to make sure we have clear in our minds. The difference between displacement and distance. They sound very similar, and a lot of times they might describe somewhat of the same thing, but they are not the same. The displacement of an object is both the magnitude and the direction. However, the distance is just the magnitude. Okay? So, for instance, let's say we throw a ball straight up and then catch it. So if we throw a ball straight up into the air and then it comes back down and we catch it in the same position, if we look at what is the change in position, well, it's zero. There is no change in position because it left our hand and then it came back to our hand. So where it started is the same place it ended. However, the distance traveled is different. It traveled some distance up, and we can call that x or y or whatever you want, and then it traveled that same distance back down. Another way you can think of it is that displacement is independent of path. It only looks at position, where distance is dependent upon the path. It depends on what path you take to determine the distance that you travel. The rate at which an object moves can be described as speed, and we say the average speed of an object is defined as the total distance traveled divided by the total time elapsed. And so if we take the path length, and this is important, that is the path length, and we divide by the elapsed time, we get the speed. And once again, speed is a scalar quantity. So think about the speedometer on your car. When you're driving down the road, it tells you a speed that you're going, which is in miles per hour, which we will not use typically in this class. We will use meters per second or kilometers per hour because those are the SI units. But that tells you a speed you're going. Does not give you direction, does not give you anything but the relative speed that your car is traveling at that moment. Average speed totally ignores any variations in the object's actual motion during the trip. The path length and the total time are all that is important. So it doesn't matter if we have any twists or turns, it's just totally dependent upon the path length, the distance traveled, so the reading on your odometer, and the time that it takes to travel that distance. Both will be positive, so speed will also be positive. So since the distance traveled is positive and the time that elapses is positive, the quotient of those two quantities will also be positive. And as I mentioned before, the SI units are meters per second, and sometimes we'll even jump up to kilometers per hour. Velocity, however, may look the same on the surface, but is very different. Velocity is the time it takes for an object to undergo a displacement. So right off the bat, instead of talking about a distance traveled, it's a displacement. So this is a vector instead of a scalar. And so velocity itself will also be a vector. Okay, because the velocity is the displacement, the delta x, divided by the change in time, or the time that is elapsed. And so since we're going to have a direction for our displacement, we will also have a direction for our average velocity. So velocity can either be positive or negative, because delta t is always positive, time is always increasing, and so depending on the change in position, that direction will also be the same direction as the velocity. Average speed, and this is very important, average speed is not the same as average velocity. As mentioned earlier, the direction of velocity will be in the same direction as the displacement, and for now we will just use positive and negative to determine the direction, whether it's in the positive x or the negative x, and the units are meters per second. Now other units could be given to you, but you will have to convert them. Some other units that you may see are feet per second and centimeters per second. To illustrate the difference between speed and velocity, we can look at these two different paths. We have a blue path that follows a sinusoidal path or a convoluted path, and we have a red path that is much more direct and linear. So cars on both paths have the same average velocity, since their change in position or the displacement is the same and the time interval is the same. However, the car in the blue will have a greater average speed since the path length is larger than the path length of the red. So the same average velocity but average speed has to be greater in the blue. Of course, this is all assuming that both paths occur over the same time interval. As I mentioned earlier, we can pull a lot of information off of position versus time graphs, and velocity is one of those. So if we have a position versus time, we can take velocity from that graph, and the average velocity is the slope of the line joining the initial and final points on the graph. And an object moving with a constant velocity will have a graph that is linear. Looking at this position versus time graph, we see that the linear path here shows that it is a constant velocity because the slope from A to B, the slope of this line here, is the same as the slope from B to C. And so the slope is telling us the average velocity, and since the slope does not change, the average velocity does not change. And this should make sense. How do we calculate slope? Well, to calculate slope, we have rise over run. Our rise is delta x, our run is delta t. So the slope is delta x divided by delta t, which is average velocity. So we use this general equation to say the change in the vertical axis, which in a position versus time is going to be delta x over the change in the horizontal axis, which is delta t, and that is our average velocity. And keep in mind, slope carries units. It's the vertical axis units divided by the horizontal axis units. So if we have meters and seconds, it'll be meters divided by seconds. So if we go back to the graph that we had earlier, where the average velocity is not constant, we can see that the slope from A to B and A to C and A to D and A to E and A to F are different. They're different slopes, meaning the average velocity from those points are going to be different. We can also note the slope is either positive or negative, and we see that we have positive slope from A to B and positive slope, even though it's a little less, from A to C, and negative slope for the others. And so we see that our average velocity changes from positive to negative as we go along, as time continues, and we go to further and further endpoints. Now, in your book, you're going to see an equation that looks like this and says that the limit of the average velocity as the time interval becomes infinitesimally small, or as the time interval approaches zero, that gives us the instantaneous velocity. All right, now this deals with some calculus concepts or some higher end pre-calc, so we're not going to get into that equation at all. However, we are going to talk about instantaneous velocity. We are going to say the slope of the line tangent to the position versus time graph is our instantaneous velocity. The instantaneous speed, however, is just defined as the magnitude of the instantaneous velocity. So just the number and not the direction. So if we look at this graph, these blue lines show us the average velocities at any 2 points. But to find the instantaneous velocity, meaning at that very point, what is the reading on the speedometer? How fast are we going and what direction are we going? That has to be the line that is tangent to that point. Now, we're not going to deal too much with calculations with this, but we just need to understand the general idea of the concept. In the next video, we're going to look at the third piece, or the third quantity to describe motion, acceleration.